I'll take that as a yes. So the topic we wanted to explore today was this concept of recursion schemes, which I have a feeling, I mean, depending on maybe how deep you are into functional programming, you may not have heard of it all, or I think maybe you've like heard of, but like really don't know anything more about, other than it sounds scary and I don't know what I would do with it. Or maybe there are some people who are experts on it and can jump in here. But what we're going to try to do is motivate the concept in a pretty accessible way, and then try to talk about one way that you could actually potentially use this code in a way that is still pretty accessible for yourself and your users. And I think a little bit of, the thing that is cool about this is there are at least one data structure in Zio that I know of that you probably work with pretty regularly that actually uses these recursion schemes, but it's done in a way where you probably wouldn't even realize it. And it's the spec data type in Zio tests. So every time you do one of those like tests or suites or use a test aspect to work with them, under the hood, that spec type is actually one of these recursion schemes, or one of these fixed point data types, which sounds like really scary. But I think part of the credit of that approach is you kind of work with it and you basically get to work with it like it's a normal data type. So we'll start with just kind of motivating it, and we'll kind of build up to that. And so I think maybe a helpful way to start is with actually something that came up in one of Kit's last times talking about. Wow, look at that. that is funny.
Wow.
Okay, we are not going to do either of those two math problems, but that is cool. Anyway, but I guess those do both use recursion, so you can kind of understand how Copilot came up with that. But I think one of the concepts talked about there was this idea of a fold, and that a good criteria for a good definition of a fold is that it handles all of the constructors of a data type. And so that if you actually fold with the constructors, you get the data type back. And so maybe to start with, we can just explore that a little bit. And so a really simple one might be, we could define something like fold option. And so this will take option. That's an option of A. And then here we could have these two cases, and maybe we could call these empty. And this will be a B. And maybe even to make this more clear, I'll make this a unit to a B, at least initially. And then we're going to have another case of sum. Maybe I'll call this none. Sorry, I forgot the actual name of these. And this will take an A to a B. And this will give us a B back. And so here we could just do option match. And if it's none, then we just call none. And if it's sum, we just call sum. And the only real reason, I didn't even really particularly need the laziness here for the B. I just kind of wanted to emphasize the idea that these are both functions, and it's just this none thing has no information. So we can use the unit value there. And in the actual signature, we delete that because we don't need it, and we curry these, but I'm going to leave it here just so we can kind of see some common structure here.
Yeah, and sometimes we have it just be a call by name parameter, which is essentially a thunk.
The same thing, yeah. And so here, if I had something I could write identity option, and I could say, well, if you give me any option, I can just give you the same thing back. And all I'm going to do is I'm going to do that fold. And if it's a none, then I'm going to give you a none. And if it's a sum case, I'm just going to put it back in the sum. And so this is always just going to give you the same thing back. Whatever I put in, I'm just going to give that back. And we can kind of play with that a little bit more. And maybe we'll do either next. We'll just do a couple of these just so we kind of see the common structure. So here I'm going to start with an either EB or AB. And again, I'm going to have one case for each of the cases of this data structure. And right now I'm just going to try to mirror the names of the constructors. And so again, my implementation can be, in this case, pretty simple. if it's a left, then I'll just call the left function on it. And if it's a right, then I'll just call the right function on it. Relation going here just so to make sure I'm not cheating.
I'm just going to rename those summary types to Z so that we can sort of see the similarity there.
Oh yeah, yeah, I think that's a great idea. And so we could do identity either here. And so again, if we folded and we just put them back in the constructors, we would get the exact same thing back. So far, these two are both like pretty simple because these actually don't have any recursive structure to them, right? The option is just either an A or a none. There's no further like option inside the option. And similar to the either here is just, it's an A or B. There's not like an either inside the either. We can explicitly make one, but it's not built into the structure. But we can do the same thing with data structures that are recursive. And so I think like the other one we probably hit on when we were looking at it before was this fold on a list. And so here we have this list. That was a list of A. And the list has, I guess we'll call it maybe nil. And this is another one where there's no information there. So we can just use the by name parameter, or we could just even get rid of that entirely. But I'm just going to leave this here just to kind of be like super explicit here. And then we're going to think about the fold right as the kind of canonical, like it's not stack safe, which is why I don't use all the time, but in a way it's like the most canonical like instance of the folding on the list here. So here we're going to get a and a B to a B, and we're going to get a B back. So just match on the list, and if it's empty, then we can just return this. And if it's fail, then we can put this on the head, and then we can do the rest of it. And again, if I could do identity list here. And I could say if I folded over the list and I returned nil when I had nil, and I had head and tail, I just put them together into this cons case, I would always get the same list back. And let's see, what have we got? Got one here. I think it's just me. Should be.
Oh, and then there's the A.
Oh, A list, right. This is when we make things. Just these freestanding methods versus normally it would be like a method on a list, but we're just kind of avoiding doing the extension method thing. So the one thing that's a little bit different and noteworthy here is in all the situations above, in the like the fold either or the fold option case, the Z here only appeared on the right-hand side of each of these functions, right? So this just like took an A, gave a Z, this took nothing, gave a Z, this took an A, gave a Z, this took an A, gave a Z. And this list case is the first time where the Z here appears on the left-hand side. And that's one clue that this is a recursive data structure here, because when we're doing our fold, this Z is representing essentially everything we've folded so far. So this Z was conceptually, this was originally like the rest of the list that we haven't processed yet. And we're taking that, and because we're doing this fold, we've converted that to a Z here. So that's what makes this different being a recursive structure. Is you've got the Z on the left-hand side in addition to the right-hand side. So like, I think we get pretty used to this signature, and normally we'd actually call this fold right instead of just fold list. And we'll see very similar things on other linear data structures. So I could define a similar fold on a vector or a chunk or if I don't care about the order, I could fold over a set or a map. So this ends up being a pretty common signature, but there's actually nothing unique about this to these lists or these linear things. I think we see these most often because, like, if you look in the Scala standard library, you basically only have these types that aren't recursive, like option or either, or you have these types that have this linear structure like a list. You don't have any types that at least you work with at a user level that contain some type of recursive structure, but that have a more complex structure. So, for example, to take like a simple example, we could have something like some tree that has, oops, what's that?
I just said treep because it a treep. I don't know.
And I mean, trees can be a little bit tricky because there can be all sorts of different types of trees that have different structures of branching or not. But I think one like pretty simple one we could do is we could say we have a leaf that just has a value, and we have a branch that, and I mean, we have some where like there's another value in here, but with this one, let's say at least for now, like it doesn't, it just has these two values on the left and the right. And so we could think, well, okay, how do we write a fold function for this? And we could basically do the same thing. And this time, since I've defined this data type, I'm gonna, and boy, I almost feel like I need to like disable Copilot here because it like takes all my thunder away. But so we have these two cases, and maybe I'll be even more just incremental here. So I'm just gonna make this nothing type just so I can do this a little bit more incrementally. And sorry, I'm not telling why I did right, but we have these two cases. And so like, this is the simplest, like, okay, I've got this thing, it has two cases. So I need a way of handling each of those two cases. And then we can basically just say, okay, well, anytime I've got any values that are just ordinary values that aren't other recursive cases in here, I can just have a function from that. So like here, this like leaf case is just a function A to Z. And then anytime I have a case that has some recursive structure, I just replace that with another Z. So like I could call this like ZZ to Z. And then I could implement this in my little self type. I could say self match. So I've either got a leaf or a branch. And so if it's a leaf, then I'm just going to call this leaf function on the value inside there. And otherwise, I'm going to call the branch after I fold over the left and the right. And maybe to make this like a little bit more concrete, we could just like show ourselves like a really simple example here. So like one thing we might want to do is we might want to say like how many leaves are in a tree. And we could fold that and we could say, well, if it's a leaf case, I've got one. And otherwise, just add them up. And so then I could do something like, oh, look at you, you're already ahead of me. So then I could do like print line, example tree dot leaves. And hopefully we got 4 here. Let's see, well, first let's resolve our compilation issues. Oh, yep, we need our little, okay. So now I'll run this. And this was 6.
We have so many now.
And there we go. And we've got these 4 leaves.
And this is generally why folds have multiple parameter lists so that we can affix the input type and it can infer it a little better, like this.
Yeah, though I think this one is actually still going to have trouble with because this is a, well, let's see if maybe we can do that. Maybe you're right.
Oh, well, I'm going to fix these. Oops.
Yeah, let's fix these. But yeah, that is exactly right. A lot of times we can query these to improve the type inference there. I was kind of trying to just not do that just so we made it a little bit easier to see the common structure, but I think that's a great thing to show. So let's, yep, and now we're able to get rid of that. And now if I can remember, we are at 6, and there we go. So we get the same thing. So one thing here, I think, even before we get into anything more advanced, is just like, I think this is more good practice and techniques on this idea of how to create a fold for a data structure that is a little bit more complex. And this is something that'll really scale with you for as you build in more and more complexity. So like you could imagine maybe this is actually, we want to have a value at each of these nodes. And so now all I would say, okay, I've got a recursive case, I've got an ordinary value, I've got a recursive case. So Kit's done exactly the right thing. He's put an A in there. And now I can just re-implement my fold the same way. And I think now the only thing we need to do is we need to, yeah, we need to give these guys some, let's see, what do we do? Okay, so we can do this. And we still get, because we just wanted to count the leaves. But we see here that part of the advantage of this is it gives us all the structure of like here, we kind of, in a way, we didn't care about the branches other than we wanted to kind of add up the things from the leaves, but we could have more complex logic here. If we wanted to, we could do something like we could say, well, this is, we want to sum this, and let's say that we want to have like a numeric instance of A, that's this type class that in the Scala standard library that kind of lets us describe this. And I think we might need to, oh, well, this should give us an A. There we go. And we might need to import, I think it's like Scala math numeric dot ops or dot implicits dot infix numeric ops.
Nice. Does that need to be A1 there?
Yeah. Oh yeah, that can be, yeah, A1. This is type A. Oops.
Scala must be stated with symbols.
Yeah,
Right.
and then let's see.
Font A. Oh, because it doesn't know that.
Oh, I think we probably, then we may need to do something.
Oh, the A1 there.
That, I think, yeah. So yeah, this is not recursion scheme fanciness. This is Scala fanciness. But so now we have this operator where we can sum this thing, and we can kind of take advantage of, okay, the leaves have this structure, and then there's also this other value here. So let's try this.
Yay, 23.
Now we got 23, which I haven't checked, but seems
Yeah, that looks
correct.
right.
Yep, I think that is correct. So excellent. So yeah, so you can kind of create these folds for whatever data structure you have, and as complex as your data structure is, you can just have more complex folds. But what we can sometimes run into a little bit is that at some point, this kind of gets maybe a little bit complex. So like if you, let's try playing with something like Zio has this cause data type. So this you might have worked with in Zio if you kind of have to work with like the full cause of failure of like, is it a die, is it a failure, is all these things. And so it's got a whole bunch of cases. So, and it's been refactored a little bit over time. But so I think one thing we could say is like, okay, it can be a failure, or I think we just call it fail, which has like a typed error. It can be a die that has a throwable. And then we also want to have these more complex cases where we want to be able to run this concept of parallel errors. We want to be able to represent some concept of having sequential errors. So like this error occurred before this error. And then we even want to be able to have this concept of like adding like tracing information. And this has changed a little bit between ZO versions, but just to kind of give us something to work with here. Right now, I think I'm just gonna say trace is a string. And yeah, we can have, so basically this lets us just attach this like tracing metadata to any other cause. And so you might think about like, okay, how do we do a fold for this? And the positive is we can kind of follow exactly the same techniques that we did before. But we'll also see, I guess, a little bit of the pain point of this. So we could say, okay, with a fail. And another thing we sometimes do is it can be nice to call these cases when they get a little more complicated. So right, this is like handling the case where it's a failure. So we could say, okay, I've got a fail case. I've got a die case. I've got a both case, a then case, and a trace case.
Sorry.
No. And so we can apply exactly the same technique here. So a fail case is, we saw the fail has an E inside it. So this is going to take an E to a Z. Die case has a throwable. So it's going to take a throwable to a Z. Both has two causes inside it. So those are the recursive cases. So we'll replace those with Z's. The then case is the same way this way. It's just got the two Z's. And the trace case has a Z and a trace. And there we go. And one of the nice things is, at least if we're not worrying about being stack safe, there are ways to do this in a stack safe way. But if we're not worried about that, then most of these implementations are pretty easy. Basically, if we get to any of these cases that aren't recursive, then we just call the case. And otherwise, we use that case and we just call this fold on each of the other ones. Now, these are going to get a little bit long because these are going to need, we need to pass through all these cases. So this is going to be like fail case, die case, both case, then case, trace case. Similarly, exactly. And similarly here, I'll just copy this. And yeah, now exactly, you can basically just copy that. And let's see, I think maybe I might some parentheses here. Okay, let's get auto compilation. Okay, cool. So, I mean, the good thing is we've got a fold for this relatively complex data structure that, I mean, maybe if we hadn't done this before, you wouldn't know like how to write a fold for it. And the implementation was, I mean, it's a little, I guess, decent, not a trivial number of lines of code, but it's honestly like pretty simple. We could follow this pattern that was pretty straightforward and hard for us to mess up. So that's all nice. But what we can also see a little bit here is like, okay, these signatures are getting a little bit long here, where we have to handle every one of these possible cases explicitly. And one that just kind of gets to be more stuff, especially as our data structure gets more complex. I mean, this is probably not even the most complex data structure we would deal with, but also in a way we don't get to use some of our nice tools here. Like I might say, it might be nice if I could do something like, let's say I just want to count the number of failures in here. So it might be nice to kind of treat some of these the same way, to say, well, for any of these, just do something else, right? Or maybe I want to get all the throwables and just say, well, if it's a die case, then give me a set of the throwables. And otherwise, if it's another terminal case, just throw it away. But it's a little bit hard for me to do that with this construction. And if we step back a little bit, it's also, we can kind of see like there's a similarity, right, between all of these folds. And I think we've tried to make it pretty explicit of like every one of these folds, whether we've got this like fold cause, we've got the fold for the tree, we've got the fold for the list, we've got the fold for the either, we've got the fold for the option. They all have a very similar structure, right? Of like, they take a data structure and they take some set of functions that handles each case of the data structure. And we saw there are these like very mechanical rules of like, okay, they always return the Z. They always take in whatever is inside that case of the data structure. And if it's a recursive one, they take in the Z themselves. So like, there's a lot of similarity here. And one way we can just exploit that is kind of, I guess, what we've done in some of the other things we've talked about, of just like recognize that and just take that as a tool in our own code design. And in a way that may be like the most practical thing you take away from this. We are going to get to like the actual recursion schemes, but I think in most cases, probably like the way you're going to get value kind of on a day-to-day basis is just being able to implement these folds for more complex data structures, and then having that ability to kind of work with them and having this common operator to deal with them. But you might say, well, okay, that's all well and good, but like, we're doing programming, we're doing functional programming, we're trying to have abstractions here. How could we try to generalize over this like common structure of like, we have this method that has, I mean, maybe I give it a different suffix, but it basically has the same name in all of these things. It has a very similar concept, but right now we clearly like, we can't make them actually the same because they all have different signatures based on all these like different cases that are like totally specific to the data type. And so the idea of these recursion schemes is, if we look at this, we could kind of say that this is actually, maybe it's actually combining two different concepts. And so one concept would be the concept of recursion, of this idea that like, we've got this whole big recursive data structure, and we want to like keep calling this fold method as we get to each of these recursive cases, and then we want to build it back up again. And then the second concept this is building in is this idea of the structure of the specific data. So like the fact that this one, there are 5 cases and they're called fail case, die case, both case, and this one takes an E and this one takes a throwable, and this one has 2 recursive cases. And the fact that we're like doing both of these as part of this same function here is what's stopping us from being able to like further abstract over this and like unify all of these folds into the same concept. Does that make sense to folks before we move on?
Sounds good so far. I mean, let's see. Let's get a
yeah exactly. Okay, so to try to accomplish this, what we're basically going to do is we're going to try to separate out the recursion from the structure of these specific cases. And so the pattern that we've used in ZO libraries that I like, and maybe I'll take this whole, let's see, maybe I'll, let's, take this whole thing, I'll just put it into another scope just so I can do another version of it. Just make sure I haven't, did I blow everything up there?
I think trace, no, trace is fine.
Where's, yeah, what did I do here? Oh, these all got imported at the top. So
I just move that into
bring that into, yeah, exactly. Okay, great. We're back in compiling. Okay, So the pattern we follow when we do it this way is we're going to start with these cases, and we're going to define the cases separately. So we're going to define this thing that I think right now I'm going to call cause case. And we're going to take each of the things that were previously just cases of cause, and we're going to make them pieces of this cause case here. And the only thing I'm going to do differently is every time I've got a recursive value, I'm going to replace it with a new type parameter I'm going to define here. So here, maybe I'll call this EA. And then just to kind of make these more clear, I'm going to call them cases instead of their previous names. And then every time I've got one of these recursive ones in here, I'm just going to replace it with one of these A's. And then once I've done that, then yeah, and then I'm gonna have to see what do I actually need here. In some cases, I may not need all these type parameters here. And then anytime I'm not using a type parameter because I made these covariant, I'm just gonna use nothing instead. Okay, so let's just make sure we got this. Oh, and then these are going to be A's.
I think we want trace outside of the, oh, it says trace is string. I'll just put it up here.
Oh, yeah, yeah, we just need to, yeah, perfect. Okay, so what you notice we've done here is we've tried to separate out this concept of the structure from the concept of the recursion. And so now all of these, this new cause case thing we created, it's now not a recursive data structure anymore, right? There's no case of cause case that itself refers to cause case. There's just this like A inside it. So this is not a recursive data structure anymore. This is purely kind of describing the concept of like, this thing has two things inside it. This thing has two things inside it. This thing has one thing and a trace inside it. This thing has a throwable. This thing has an error inside it. And the other thing that's going to be helpful for us here is we can define a map function on this. That's just going to take any A to a B, and it's going to turn a cause case EA into a cause case of EB. And so I can just match on these. And then the only times I'm really going to have to do this is when I've got one of these A's inside. So like here, fail case E, the fail case E doesn't have an A inside, so I just return it. Same thing for the die case. Oops. Sorry, I think so I screwed myself up and I screwed you up.
Oh,
Not case. That's a different thing.
Well, I had Copilot put that one in, so it probably was biased.
Oh, and these can just be F of A.
Oh yeah, yeah. These are just
right, because it's not recursive anymore, right? That's kind of the that's the mindset shift of we've taken out all of the recursion here. Oh, and I think these are called causes. Maybe I should rename these, but that's fine. Okay, so now we've got this thing compiling. So then our question is kind of like, okay, how do we get back the actual like recursion here? Like right now we've just got these cases, but we don't actually have the recursion. And so here what we do is now I'm going to define our cause case class. It's going to take an E, And it's going to have inside what we normally would call like the case value, which of these cases it is. And this is going to be a cause case of E and cause. And that last part is, oops, let's see, what did I do wrong? Oh, I just need to import.
I think cause case dot cause case, cause dot cause case. Because
Yes,
that's inside
yes,
of the,
yes, exactly.
or rather, just I think just without the.
Yeah. Okay, and this will be cause of E. Okay, and this is where like this approach can get a little bit mind bendy, especially when you like don't do it with a kind of concrete type, but like you may have like seen in some, if you've ever like read about this, there's like a fixed type, and like I would say that gets like even more mind bendy, which is why like I like to start with this, which is basically just kind of a specialized version of that. But so what we're saying here is this cause, it contains inside it one of these cause cases. So every time we look inside a cause, it's either a fail or a die or a both or a then or a traced. And the A type that's inside it, if we look in like a both case, is itself going to be a cause. And so this both might have two different causes, and those might each have inside their own cases, which might be fail cases. And so maybe a helpful way just initially to kind of make this a little more concrete is a little bit, self can be a more helpful.
Yeah, Damien recommended that. And I you've seen that.
Yep. Yep. Yeah, and I think especially with the A kind of being the value type, that's a good one. Mm-hmm. So I think one thing that maybe we can do here just to make this a little more concrete is the same thing we did with like the example tree of like, let's create an example cause. And we're going to start by doing, in a sec, we'll create some like nicer constructors that'll like make it look prettier. But like first, let's try to like actually do it like the full way. So if we want to create a cause, it's just a case class. It's just this one case class that has this one thing inside it. And that one thing inside it is one of these case values, which are just like the fail, the die, the both, and then the traced. And I think right now I'm going to do, oops, what do we got? What did we just?
Oh, because that's, oh, I see. That's just inside of the cause object.
Yeah. Okay. So because I don't want this to be too boring, we'll do the, this will be the, we just do the both case. And this is going to have two things inside it. And then these two things inside it are themselves causes. So this might be like a cause. And that's a cause. And then here, maybe this is where we get to the point where we're kind of done, where like this is a fail case, fail, and yeah, that's a die case, die. Nice.
Oh, that needs something.
And fail case. No, it just needs me to spell it correctly.
Yeah, the cause case class, the case cause case class, very tongue twisty.
Yeah. So, I mean, we'll get a little bit to some of the benefits of this, but like before and we'll also make this like prettier to construct these. But before we do that, I just want to kind of unpack this type signature can seem, this type signature can seem like kind of scary here of like, we've got a cause, it's got a cause case inside it, and the cause case has another cause inside it. And like, does this ever terminate? Like, what does this mean? And hopefully this gives you a better sense of how we're kind of encoding it definitely in a particular way to kind of get where we're going, but that it's actually not that complicated. We're basically just going back and forth between these cause constructors and these case constructors. And we just kind of keep bouncing back and forth between them, right? From like cause to both case to cause to case, until we either get to a case that is a terminal one, or we just keep going potentially forever, but then we're probably not going to terminate, at least when we have strict structures like this, and it's not going to be very fun. So what Kit is going ahead now and doing is he's doing exactly the right next step here of, if you're following this pattern, what you then want to do is you want to create these little, technically smart constructors, but these little nice constructors that let you and your users work with this data type in a way that feels very much like a normal data type. And so all you do is, when you've got these terminal cases, you basically just stick whatever value would normally go inside the case, and then you just wrap it in another cause. And so like if we look at these constructors here, these now look exactly, I mean, if we didn't look at the implementation, if we just saw the signatures, these now look exactly like the constructors that we would have on the previous data type. And in fact, I mean, maybe we can do that. We didn't need them as much on the previous one because we could just use the apply method on the case class. But if we want to go back here to cause, and we might actually do this sometimes, if we kind of wanted to have either like better type inference, or we just wanted to make things a little bit simpler, but we could have all of these be like, this would just be fail with the error. This would be die, throwable. This would be trace, with the cause and trace. There we go. And so we can see at this point, we've like, at least so far just for the constructors, but at least for the constructors, despite having this like more complex encoding, we've now gotten back to the point where the constructors that our users can use are actually exactly the same between these two different approaches and feel as natural. And so like here, like, oh, I think, okay, so I think, yeah, it's already on top of it. Like this, I mean, was good for kind of educational purposes, I guess, but is like kind of ugly and painful. This is like, I think, as simple a way as you could write that. And right now, these are constructing exactly the same thing. So, okay.
And the reason it terminates, just for the same reason as when you use normal inductive data types, is that some of the branches of that type are sort of just, they have nothing as that parameter. They're leaf cases. So we always have to end with a leaf case, a terminal case, like the fail or the die case that did not contain the recursion. And so it's okay if the data type's recursive, because in some of those cases will terminate eventually. As long as you can construct an infinite one, but then you're going to just blow up.
Yeah, and we can't even, I mean, this one can terminate because it has terminal cases. We could even construct a data type that has no terminal cases. Mm-hmm. So we could think of like I think in like Haskell, there's one variant of like their stream type. It's like an infinite stream that like it always has a next element. And so there's like never one that doesn't have a recursive case. And if we were sufficiently lazy in processing it, we could do that too. But I think that's kind of enough of another case that we've got enough other things going on here. Maybe we could save that for an exercise for another time. So, okay, we've got this, hopefully we like understand at least a little bit of this complexity. We've, I think, recovered some of the simplicity on defining it. The thing we haven't done yet is we haven't looked at the fold method here, or a little bit of the potential payoff from this. So let's look at this now. So now if we want to define a fold, we get a little bit of the payoff here. Because now we get to define this F. And before, like the fold had to handle each of the cases of the cause. And so it had to have a separate parameter for them, right? So if the cause had like 5 cases, in our signature up here, the fold method actually had 5 different parameters, which is like an argument for each of these. In contrast here, like we start to now get the benefit of having factored out these cases into this own trait here, because now what we get to say is that this fold gets to take a cause case, EZ to Z, and it's going to give us back a Z. And so now we've kind of collapsed those like 5 parameters into 1 parameter. And I mean, in a way, we've just kind of moved things around. But now essentially, since this cause case has these 5 possibilities, we are able to describe one function that can cover all of those cases. And so like here, if we think of how we'd implement this, I can say, well, all this cause contains is a case value. So like, I think one of the things you'll find is like some of these operators can be, again, a little bit like mind bendy when you like first implement them. But like a good like way to think about it is like the cause doesn't contain anything except the case value. So if you want to do anything with the cause, like you got to start with the case value. And the case value only has these 5 possibilities. So I could say, okay, well, let's match on the case value. And let's think about what I would do in each of these cases. So these ones here, like this fail case, well, if we go to the fail case is already has nothing for that recursive type.
Mm-hmm.
So we can actually already, this function that we gave it is already powerful enough to handle the fail case. So here I can actually just do f of fail case of e. And yeah, maybe we can just do questions here just to, oops. Yep. Another pattern you may sometimes see here is you may see someone do something like this. This is a very, I would say, a little bit of a micro optimization. What this is basically doing is it's saying, let me avoid constructing this intermediate fail case because like all this thing and this thing are the same. So instead of unwrapping it and then putting it back together again, I can just use this @ symbol to basically refer to this thing, and then I can just stuff it back in here. So it's a little bit of an optimization, but I think I would recommend when you're getting started, like don't even worry about that. I just point it out. So like if you see it, you kind of know like what that is and like why it's there, but also why in a way it's not that important.
Mm-hmm.
So, okay, so now let's look at like the both case. So this one's a little bit more complicated because it's got the recursive cases in it. But so this is where we handle the recursion. And so this one, we could say, okay, well, I've got this left thing, that's a cause of E. And ultimately, I'm going to need to turn this into a Z because I'm going to need this to be a both case of Z, so I can call F on this. So I can do that first. And then I can just call fold again on these. So here I could do left.fold F, right.fold F. Yeah, we can do the same thing in the trace case. And so you can think in here, we've like, so also this is like so here we've done this in like the most explicit way possible, where I've dealt with each of these cases. But if I want to, I can even do this.
I'm going to call F on that, right?
Yeah, exactly. Thank you. So this is like the super simple version of this.
Yeah, and the more boilerplate.
Right, and so here you can kind of see where you like start to get the payoff for this work we've been doing, because now this fold doesn't really know anything about what this cause case is. Like the cause case knows about it and its map function knows about it, but this fold doesn't really have to know about it at all. And in fact, if we wanted to abstract even more, we could like not call this cause case. We could not call this thing cause. We call this like recursive. That's the like Zio prelude version of this. And then we could define this one time for everything. But I think that may be maybe one step at least farther than we want to take right now, because I think we probably want to explore this idea a little bit more.
And just, I thought that was a good idea to first show this explicitly, because basically if we look at how we implemented this case, it is exactly a map, really. Like
Right, exactly. Map is building in that logic for us in one place. And that's kind of why, and we may go back, we may implement like a for each or something, but that's kind of why there's value in like doing this, because you're kind of building in like all the knowledge you need to have about the cases within this cause case. And then at this level of like cause, or if you wanted to generalize even further, like recursive, you don't need to know about that at all. You can just call those operators on it. So sorry, go ahead.
Oh, I just said sweet. Cool.
So with this, let's maybe try to implement a couple of, so I think we did a couple of these operators. I think we did one for failures and defects. So let's like look at how we can implement these in terms of this. And I think this will also just kind of show a little bit of what's even just conceptually cool about this. So we've got this, so we got this fold, and the fold usually does need, especially when you're doing it with these recursion schemes, it usually does need you to provide the type parameter here, because you can see here the Z appears as both an input and an output. And so the Scala compiler has a hard time inferring that when it's an input like that. So you usually will need to specify that Z type parameter there. So we're going to fold, we're going to produce a list of E's. And so one a little bit of, I mean, in some cases it matters more and less, but we don't need 5 different parameters here. We now just have this one function. And a really nice way to implement this function a lot of times can be, we can just do like this inline pattern match here. And so I think Copilot is on the right track here, but we'll just go through some of these. So if it's a failure, then I'm just going to put it in a list. If it's a die case, then I don't need to do anything.
Sorry.
No.
Ah, yes. Editing one line away seems to magnetize the cursor.
So let's look at these both cases for a sec, because this is where this gets kind of a little bit cool. I would say, at least when I like learned this, I thought this was cool. So say we've got this, and just hover over these things. So now that we're looking at a both case, but the left isn't a cause or a cause case anymore. It's a list of E's. And so at this point, kind of my work, at least in this, is like really straightforward. I'm like, well, I'll just plus right. And so this, I think, gives like a pretty like nice way now of defining these things, where you can again see a little bit of this like separation of like the fold took care of all the details about like processing the recursion for us. And so by the time we're handling like this both case here, it's already done it for us, right? It's handing us this like list of E's from the 2 recursive cases on a silver platter. And it's just saying like, hey, what do you want to do with them? And in this case, I can just combine them, but I could also do other custom logic, whatever I wanted with that. And then we could do the same thing for defects. Yeah, except this time we'll get a list of variables. And there we go. And so this is starting to get to one of the things that, so one payoff of all this is getting to define these in like this like pretty consistent way. And as you go down this road, there are like more and more advanced versions of like collection-like operators that you can define here. Of fold itself is already pretty powerful. It will kind of let you do like almost anything that tears down the collection to like some kind of summary value. But there are other things that we can start to define. We could define like transformations. Yeah, we want to do the fancy words. We do the histomorphisms, the zygomorphisms, paramorphisms, and the catamorphisms and anamorphisms and all this stuff. And I mean, maybe depending on kind of interest, we can do more on this, where we kind of do like all those fancy things. I mean, so far we've really been doing the fold. We can do the unfold as well. But I think I want to just like make sure we kind of get like some of the basics first here. So one of the payoffs we get is that we get those operators. But I think the other thing that conceptually is a little bit different with this, that you can express this way that you couldn't express the other way, is you can have these cases that have some additional information associated with them. So like, let's say that we wanted to say that we had our causes down here, and we wanted to like annotate each of these fields within the both with having some additional information, with maybe having like how many, like what's the size of the cause below that. And in the original encoding, it wasn't really possible for us to do that, because the both is hard coded. Of the both has a left cause and a right cause, and it has nothing else, right? It only has these two things, and the cause, we know exactly what the cause is. It's one of these 5 things. So like if we wanted to attach additional information to it, we don't really have a great way to do that here. Versus in this encoding here, we're starting with this cause where each of the cases has a cause inside it, but maybe that's not where we have to end. Maybe each of the cases, when we're done, is going to have a cause inside it, and is also going to have some other metadata. Is going to have like some information on like the size of that tree or something like that. So that's like another interesting thing that you can do with this that you can't express in quite the same way with that traditional encoding. So maybe that would be a fun thing for us to explore here. So let's play with implementing. If we can do something that will be like a transform that'll take us from, do a cause case.
Do we want to change the error type there to Z?
No, sorry. Yeah. Oops, sorry, hold on a sec. Okay, so we got Z here, and we'll set, but now this is going to be Z. Okay, so let's think, and again, like the way we always, we can do the math, but especially when we're kind of initially implementing these things, it can be helpful to just think about the case values here. Oops. Let's see if I can get the exhaust. Okay. What are we? What am I? Oh, Let's see if we can implement this signature now. So if we've got a fail case, then I can just call it now. On the fail case,
what does it say? It's unhappy here. So it looks like it wanted a Z, but it found one.
It found a
causes Z. Acquired. Found cause case. Oh, E1. Oh, does this have to be? Does this have to? Okay, yeah.
No, I think I'm still off here.
Does the beginning have to be E1? No.
Hold on. Let's see.
Oh wait, because it says it required just a Z, but it found a cause of Z. Oh, because I think we're translating it into a cause of Z.
Oh, there.
Is that right?
Yes. Yeah. Okay. So then this could be the die case. Okay. And then here, so now we've got two causes of E. And so I can transform each of those into a cause case. So I can do left. And this is a little bit like what I was saying before of like, I find like implementing these initially can be like a little bit mind bendy, I could say. And then I think we need one. Let's see.
Does these need to be causes again?
Yes.
Fun. Lots of wrapping and unwrapping. Oh,
exactly. And no, I think we're still.
Oh, we need to call transform
a little bit off here.
On that.
Oh, right.
There is no transform internally.
Let's see.
Oh, no, not quite.
No, I think.
Oh, because the cause of Z. Oh, yeah, and there is no transform on that. Do we just want to call F on left and right, or no? Interesting.
Let's see. Yeah.
Is this the right type signature exactly?
Yeah. I was just looking at this, and this is where it can definitely be helpful to. So I think we want to actually return another
cause, right?
Spec here. Yeah. So we want to return another cause here.
Okay.
Let me see. Sorry, we got the right.
So this should take cause.
Okay. This I think we want to be a cause. And I think at least in this case, we're going to keep the E, but we're basically going to let ourselves, like we can change a fail case to a die case or something like that. So I think that will also make our signature simpler here.
Okay.
I'm sure we actually need that constraint. I think we'll be able to say cause case.
Should these just be causes in this case? Should it be a function?
No, we want this to be a function from case to case, at least for this one here.
Okay.
So I think we want this to be.
Is that right? Oh, no, not quite. So what is left and right here? Left is a. Oh yeah, okay. So yeah, I was just confused. I could just do left. Oh wow, there. Okay.
Nice, nice.
Fun. So that just needs to change to the then case. It's easy peasy. No problem.
So this will be there we go. So this then lets us look at each of the cases of the cause and transform it to some other case and get back a cause. So why don't we try doing something with our transform and kind of play with that for a sec. So let's see, where do we, I think we've got an example of our cause here, right? Yeah, okay. So we've got this example cause. So why don't we do transformed.
This is in the wrong place, though. Let me import all of our import advanced.
Yeah.
There we go.
Okay, so now we've got example cause. And now we can transform. And so now we get this function that, like, just like when we were implementing the like the fold, we get to look at each of these cases here. So I'll just cases. And I think this is looking for probably a type parameter. Yeah, this is going to need, yeah, sometimes these do need additional type parameters. So here, let's say we leave the error type the same for now. We can play with that. And what do we, oh, this is just string. It doesn't know what E is, right? Let's just call it string. Okay. Oh, and do we need import advanced dot cause case dot all, I think.
It's just they're just in there. Yeah.
Oh, okay, perfect. Okay, great. Okay, so we're back to compiling. Okay, and so now the thing that's a little bit different than this one is, like the previous, the fold one just let us reduce one of these to just any summary value. It didn't have to, it could be an int, it could be a set, it could be whatever we want. This makes us give back a different case, but it guarantees that we give back a case and that we're going to get back a cause. So like a maybe simple example might be, what if we wanted to say untraced? And so we could see if we can do this. Now I think we got to have an example that's going to use tracing for that.
Oh, true. I'll add one to the example code.
Yeah, I'll make sure this works. Yeah.
Sorry. Okay, so I will trace. Sorry.
No, you're fantastic.
I'm slow. All right, let's do. I'll trace the fail. Trace with cool fail, and trace the die with cool die. Okay, great. Oh no, not all that stuff. All right, is that compiling? No, I screwed up.
Not quite.
What have I done? Too many parens. Trace.
I think it's traced.
There we go. Yes.
Now we have one other thing. I think we're gonna have one more thing. We're just like that.
Oh.
We need
Oh, I screwed up the paren balancing.
Okay.
All right.
Perfect. Okay. Excellent. Okay, so let's try this. Okay. And so we see we remove the tracing information from this. I'll just paste this up here so it's a little easier to see. So we see we got the rendering is a little bit more complex because we got the recursive cases. We could simplify that if we wanted, but maybe it's good for just visualizing. And so we see we took out all of the trace cases there. And I think this is actually like a pretty nice example, and maybe we can actually take it up and paste it into our main implementation here. And now let's just transform E. And I think yeah, perfect. Make sure that compiles. And so that's like actually, I mean, I think that's a pretty like nice description of like what we're doing with the when we're doing this untraced operator, right? We're transforming this thing, and we're going to look at each of the cases. And if it's a trace case, then we're basically just going to delete it. And if it's any other case, we're just going to leave it alone. And I think maybe this is one where we could try to do the same thing in the previous encoding, and we'd see we don't get to do it in quite as nice a way. So for one thing, we basically can't really define transform as an operator in the other encoding because we don't have this cause case to talk about. Like transform kind of becomes, we have the 5 different functions that kind of return anything. And then we don't get a whole lot of value out of specifying that it returns a cause because we could just return the cause if we wanted to. So yeah, like let's go up and let's, oh yeah, okay, so yeah, you're showing.
I was just seeing if we could do that. So say something like die case. Well, new error to string. Cool. And that would be cause of nothing. Can I figure that out in this case? No, it needs the nothing there.
Yeah, I think it needs that. Oh. Let's see.
I guess there is the one. Yes, because it's getting one he doesn't necessarily know. Huh, that's actually interesting.
What's the other?
Because it's a cause of E1. It's a cause of E, so we're not translating it to nothing necessarily, because it doesn't know about all the other cases and that this is the only one. So I'd probably have to go through each of them in this case, I'd imagine, if that makes sense.
Yeah, I think we might be able to make that better.
Okay. Anyway, I was just curious. It's not so important.
Yeah, but maybe what I think could be cool is just for a sec, like let's kind of try to implement the same operator as the untraced one in the traditional encoding. And so here we don't have transform, so we'll do fold. So we'll fold this to a cause of E. And now I've got to take care of all of these cases.
Mm-hmm.
And so now a lot of these ones, I got to kind of repackage things, right? Of like, this has got to be cause.fail. This has got to be cause.die, right? I think, yeah, we got to remember that these are the right ones. And then I think that's even going to have some weird issue, I think, because maybe it thinks that's, no, I think on Scalfree or something, this doesn't work because it reserves that as a keyword. So we can do the same thing, but you see it's like not quite as nice of like, one, we weren't able to express this idea of like transforming from the recursive structure to the same recursive structure as nicely. Like we had to use this fold, which was really like too general. It was like, it can just turn like the structure to anything. And then we had to like manually kind of put it back together here. Versus like, I think this one lets you express that in a way a lot more nicely of if you had anything else, then you just, you're good to go there.
And we could also do, I think I've seen like the transform sum case, which would just be a.
Right, you can have partial function variance. Yeah, exactly.
No. And then that would just be pretty easy. We could just implement this in terms of transform E1 and just do one cool thing you can do with partial functions is see if it matches. You can get the result like this. Result case other. Yay. Actually, I guess that E1 case is a little weird. Maybe.
I think we may be able to clean that up a little bit. I was just looking
Does it
at
have
that.
to be wider? Is it because it's
I
not?
was, well, I don't think that's okay. Hold on, we screwed something up.
I think we
somewhere.
deleted from transform. Just that commented. Cool.
Oh, okay. Let's do that. And then yeah. So well, it's not unrelated right now, but I think let's see. Can we do? Yeah, I think we can't do that because we have to handle the possibility where it really is.
Should E1 be a widened version of E?
It doesn't. I think if you added that constraint, I think that would work. But normally it wouldn't have to be. It could be a code kind of totally different type.
You want it to be able to okay, or change
yeah.
it.
Well, you want to be able to change it. Yeah, exactly. And so then you kind of end up with this, I think, signature here. Wait, what are we doing here? Oh, that should be E1. But yeah, let's take a look. I mean, maybe your die example is kind of interesting.
I mean, it makes sense to me why this wouldn't work because there could have been, say, another primitive case that's parameterized. Scala is not so great at knowing that fail is the only case, that
uses the
E parameter.
Right, exactly. And yeah, I mean, I think that's because what we can do, it's like not quite as lovely, but we can just grab these other cases. And then this is also where that like C syntax can be quite nice, because then we could just do.
It might be
or cause of C, I believe.
In some cases, though, because it might not know when you reuse. Sometimes it doesn't widen the error type, but we'll see.
Let's see. Yeah, let's see if we can do this. Let's see, what do we, I think we screwed some stuff up here.
Yes, it said.
I think that's next to parentheses. This is off.
Maybe I'm desynced with you. Am I desynced?
Okay, there we go.
Oh yeah, I'm totally desynced.
Oh, are you
my
desynced?
state is desynced from you, so that's probably why I'm screwing you up.
Oh no.
I see all these extra things, so I was confused. What was that?
Yeah, and so now, and I mean, right now you just kind of put it in this like two-stringed it, but like this could actually be a much more well-defined operator where like this could be, maybe we say E is a subtype verbal, right? And then, so you basically say, hey, if you have a fail case, then turn it into a die case with the error there. And so, yeah, there's a little bit of like, you're exactly right, that like the Scala compiler kind of isn't smart enough to know the fail case is the only case that refers to that, but we can make this pretty painless here, and these we should actually do like that on. But we can make this pretty painful here and describe this transformation. And there's a decent amount of logic that's being done here of it's kind of going through, it's changing this particular case, it's reconstructing the tree, and it's just, in this case, returning all the other cases unchanged. So it's making this little like surgical transformation of, maybe we can do this with our example. Do we have one of our examples with this? Maybe we need to make, we copy this. So let's say that this is a fail case with a new exception, fail. And so I'll call this example cause 3. And so this is a cause of exception, I guess, which is fine. And so then I could do print line example cause 3 dot or die. And let's do that.
Yay.
Yeah, and so you can say, see again, this kind of went through, and someone surgically went through this tree and it left everything the same, except it changed that fail case into a die case.
Yep. Cool.
So yeah, so I think that's the idea of these recursion schemes, is basically separating it out, the structure of the data itself from the structure of the recursion. And so we describe the structure of the data itself with this, like in this case, we did cause case, but that essentially would be specific to whatever data structure you're using, and would handle all the logic of like, what are the specific cases of this structure and what do they have? Do they have strings? They have ints inside them? Do they have some other thing inside them? Do they have 2 recursive cases or 3? And then you're able to define these pretty general operators like this fold operator here that work with your recursive data structure. And here we did what I think I would so in terms of recommendations, I think the most straightforward thing that probably 80 to 90% of the time you want to do is you just want to implement a fold in the best practice way we talked about. Most of the time, this, like for the investment you put in, is I think going to get you where you want to go. Then I think for the other like 10% or so of the time, you want to do something like this, where you, if you do need the recursion schemes, you kind of create your own custom wrapper type for it. Just so you can kind of have this, like everything's concrete, you can have these nice constructors on it and stuff. If you really want to go the extra mile of abstraction, then you can replace this cause thing with like in Zio Prelude, this recursive type. And the benefit is you get some of these operators for free, but it just, to do its machinery, it relies on more of these type classes of, you need to have the covariant instance or the for each instance or these different things. So, I mean, if you're like into that like style of programming, great. But just be aware that like, if you go to that level of abstraction, you're kind of going to push some of that on your users, versus the nice thing about this type of encoding is that you're able to take advantage of some of the nice things about these recursion schemes, about being able to implement these operators in this like nice way that lets you deal with these more complex tree-like data structures. But you really, it's the minimum level of complexity possible for your users, where like, you know, if you're a user of this data type, there's a little bit of complexity of, you kind of have this case versus the value, but like, if you want to work with this and you want to be able to implement things like untraced or die, like you're probably pretty happy to have transform here. And you really don't have to like know a lot about fix or about covariant types or functors or mapping or like all these things to get productive with it.
Yeah, and I think, I mean, for the actual cause, we don't use this pattern. We just
don't use that, right? Right. It's just, yeah, it's just not necessary for what we're doing. But like for the spec type in Zio test, we do, because we want to be able to express some of those transformations of specs. And doing it this way lets us do it in a way where I think, unless you like were a contributor to the code base, you probably wouldn't even know we did that.
Sure. And I guess cause is maybe a little more end user facing as well. And
a little more end user facing. And I think there's just like, I mean, as much as, you know, it's like, oh, you know, in these sessions, it's like nice to like say like, oh, isn't this elegant? Like this will do exactly the same thing. Mm-hmm. So unless you like really need to do like more complex kind of tree to tree transformations, I think most of the time you're going to get pretty far with a traditional algebraic data type encoding and just those best practices for defining your folds.
And if you're wearing your allocation hunter hat, I did notice, yeah. You know,
there are many more, twice as many more.
There are a good number of allocations because everything is wrapped a whole bunch of times.
Yeah, I think maybe you could try to make this an uneval, but that sometimes works and sometimes doesn't. So yeah. Uh-huh. Any questions before we break here?
Let's check the Discord. There was definitely some good banter. Mostly people just making fun. Good fun. Yeah, I think that's good. Naveed asked a question earlier, which I did answer in the chat or try to, but maybe it's worth just going over it. Yeah. Which is, isn't this kind of inefficient in an eager evaluation setting? For example, if I want to take the length of a side of the tree, the left side of the tree, now I recurse down the right side as well for no reason at all. And feel free to add to this, but my answer was essentially, it's kind of the same conditions as a normal fold. Like the recursion scheme are not over any kind of eager data structure. Folds are great if you want to visit every node once and exactly once. You can't stride over your data structure. You can't short circuit through your transformation of the data structure. You're going to visit every node. And you can, if you want to propagate the same value, and you can sort of treat it, the end user, you can write a function that would act the same as exiting early, except for the possibility of stack overflowing or performance implications. But internally, algorithmically, it's always going to, with an eager data structure, evaluate every element of the tree. So yeah, same trade-offs there. You're going to have to make a custom method, which might be much folk. Oops, my internet's unstable. Can you still hear me?
Yeah, you were. I was wondering if it was me or you. But yeah, so I think when you have a strict data structure like this, you're going to have a hard time avoiding it with a super general method like this. Now, you can always, if you want to, you could just implement your own method of like sum left, where you just like match on the case value, and if it's a both, you just immediately recurse on the left and you loop with that, and you kind of avoid it that way. But that is one of the things where I think having lazy data structures can let you avoid a little bit of that, because then you could, like here, if you think about the both case, like if F only needs to evaluate its left side, if like this was really fully lazy, then you wouldn't even need to do that. And you can imagine maybe a version of that where like all of these things were funcs here, but that has some of its own costs and kind of its own challenges and reasoning about it. So I think generally, like, it just makes the most sense to kind of have a bespoke operator if you want to do that that type of thing. Yeah. Anything else?
Well, next week we can deal with lazy infinite recursion schemes.
Yeah.
If the demand. No. But yeah, no, it looks like we're all good. Oh, about the problem with allocations, can opaque types help there? I'm not sure exactly. A couple of people asked about opaque types. I haven't looked into opaque types.
Yeah, I think probably so, in that you can basically make this be like an opaque type, and then you could make the cost of that go away. So yeah, I think that is a good point.
Sweet.
It'll be fun to actually be able to use Scala 3. I feel like I do a lot of like library type stuff, and so we'll be the last ones who get to benefit, because we got to support everyone until everyone else makes it across the bridge.
That's a good point. Well, thanks everyone. That was fun. Thank you, Adam, for guiding us through the jungle of recursion schemes.
Yeah, thanks so much, everyone, and take care of yourselves.
Yeah. Take care, everybody.